All right. Welcome everyone to another edition of the Tech Exchange seminar series for this semester. I am Ranga Setlur. I'm one of the associate directors of the Institute for AI and Data Science, and I oversee the community engagement aspects of it, and that involves getting the university community engaged. That's one of the missions, the internal community be aware of the research that's going on across different schools, different departments, and try to generate more partnerships and facilitate potentially applications for newer research grants that bring together people from across the campus community. And so I hope, like, I mean, this we've had some good success in getting people connected, and hope we continue to do that. So with that being said, today we have two exciting talks. We have Ryan St. Pierre from the Mechanical and Aerospace Engineering Department, and he's going to talk about his cute robots and what? And computer science, yes, sorry. Yeah, so he's also part of our affiliate of our department, and we also have Kelin LUO from the computer science department as well. And so I'll just let them go one after the other. It'll be about a 25-minute talk with some time for Q&A, and then we'll have further engagement afterwards. I think they have a few minutes, perhaps, after the talk. All right, take it away.
Great. Okay, well, thank you for having me. So my disclaimer is this is pretty new research in my group, and so this is all very untested, but it is really interdisciplinary, and it's been, really fun to work on. And on top of it, I brought a robot for show and tell. So show and tell is always a good thing. So, even if this is untested and clunky, at least I brought a robot to distract you. So lately, my group, or at least one project in my group, we've been thinking about designing effective small-scale robots for social engagement. So largely how my group thinks about robots is we think about building robots as an experimental platform. So robots are not really our end product. It's the science and technology we get to do utilizing the robots that are our end product. So this is kind of just another version of that where we've built a robot for explicitly learning about social engagement and learning about the rules of design. So the robot itself will probably never see market unless we have some angel investors in the audience. But it is very cute, so we at least have that going for us. So to kind of start talking about, especially nowadays, robots are everywhere. And one recent version of a robot that you may see out in the wild is this grocery store robot. This grocery store robot is this very towering presence that scans the grocery store aisles. And if I had the audio connected, but you would see in this YouTube clip that the person filming the robot is it's coming near them and they're like, get out, go away. So robots are deployed in our everyday life, but we don't naturally have an affinity for them. So what is going to makes robots more engaging? And I think that's kind of just been the central question that my group has been looking at. We also have pretty standard robots. Robots as workers. We've been kind of visualizing robots for a really long time. Angela Merkel is here interacting with a universal robot arm from KUKA. I assume that there's very little affinity for these types of robots. For these types of robots, generally they're put in a cage and, people stay out of the robot's personal space, and you don't want that robot in your personal space. So how do robots like this, how do we have any sort of affinity, any sort of engagement for these types of robots, especially if we're just viewing them as tools and as workers? So, what do we have to think about in order to, engage with robots in a more holistic and socialized manner? I think that, we have these types of robots and we have these visions of robots across our worlds. If we think about what does a robot look like, these types of robots usually come to mind, these factory workers. We also have robots in more of our everyday. This is my Roomba in my home. And then there's other cleaning robots that kind of go around. So these are more robots that are workers. They do tasks for us. Am I particularly socially engaged with my robot, with my Roomba? And actually, yes, but I'll explain why. And if you just have a Roomba that's like going around your house and cleaning, like, do you really care about it? How much do you emotionally invest? Are you socially engaged? This robot on the right is like another industrial cleaning robot, and at least it has eyes. So now I'm even more engaged with it, or at least personally. So this is all my personal opinions about which robots I think are cute and which ones are not. And then, we also have robots as toys. I love this space because I have a niece and nephew, and so I get to buy them all the robot toys that I want to play with. And so it's all self-serving. Like I buy them whatever I want to play with for Christmas. And so then I play around with it and then I see if I want to buy it for myself. Um, but it turns out I've been like engaged in this space since I was a kid. Like I had one of the original Furbies and it was really engaging. Like it talked back to you, it learned, air quotes on that one. And Furbies are still popular. We also have these other types of robots that serve a purpose for education. So how do we use robots to teach coding and development of our STEM skills? And, we also have this robot that's unfortunately discontinued of Cosmo. Cosmo is very engaging, and I will hopefully show you why. So this kind of begs the question, what makes a robot, or what makes us emotionally invested in a robot? What makes us socially engaged in a robot? And, there's this company called Robo Rascals where you can put a cover over your Roomba and you can turn it into a little shark, a little ladybug, anything. Does putting that on make you more socially engaged with it? Um, Maybe, maybe not. So when I got my Roomba, you set it up in the app, and when you set it up in the app, you have to name your Roomba. And now that made me very engaged with my Roomba. It is now referred to on a first name basis. My Roomba's name is Reginald, Reggie for short. So that task of just like naming it and having it as a presence in your house, like that made me pretty socially engaged. This grocery store robot, even putting these giant googly eyes and a smile on it, I still don't like it. Maybe that changes for you, but I feel like just slapping on some eyes and a face is not enough. And then the other one, Paro, is actually pretty well-developed human-robot interaction robot and particularly used for care with people with dementia so that they have something soft to pet, it interacts with them, it charges with a little pacifier. That really gets to my personal aspect of like, this is something I need to care for and take care of. And so I am very engaged with that one too. This is Cosmo, and so I'll just give you the 1 minute ad of Cosmo, and Cosmo does a lot of things that makes it all really engaging. So it has this like animated face. So it's very expressive. It can do tasks. When it fails at tasks, you feel like a lot of care for it. Like you want to take care of it. You want to engage with it. You want to, you know, play with it. And it's like this really big, deep question, like what is causing this initial engagement and what is fostering long-term engagement too? There's a lot of really interesting psychological and social aspects to robots that I personally have never considered until this project. So, again, it's more than a toy. You can, of course, use this for an educational purpose. So how do we teach students or, kids how to program with a robot that is very fun to work with? And it always gets updated. Allegedly, it had some form of AI. I don't know what it was. But it does things and it's really engaging. I think it's really cute. Fortunately, that's been discontinued. A lot of these kind of pet robots end up being discontinued for various ways or various reasons, and I don't really understand that, but maybe we'll get to the bottom of that as a collective, but hopefully we'll be able to kind of understand what makes us emotionally engaged in a robot. And so that's kind of where I kind of started this work and where we think about this overall. So hopefully, there we go. So the approach that my group has taken is just to design our own small scale robot. So I brought this robot with me today. I will plug it in and I will pass it around. And we think a lot about, how do we integrate hardware into various aspects? And then how do we use those hardware integrations to actually make our robots engaging? So it just needs a second to wake up and then I will pass them around. I promise it works. So we designed this robot. We kind of designed this, minimally structured robot itself. And, our approach was to bring all these pieces together to make a robot that already immediately has a social aspect to it. So we have an OLED screen to display different faces, different affect. We have motors underneath it. Oh no, the one time I needed the robot to work. Let me try again. We have motors, so eventually it can move around. We have a battery in the back, so it can be autonomous. And on top of the whole system is our programming port. We get a lot of questions about this. People interact with the robot and they think it's a switch. But this overall robot is about, 1 cubic inch. And so it really just asks these questions, what makes a good social robot? But really deeper for me, what aspects of design do I need to incorporate to enhance sociability and have the social aspect of robots? All right, I'm just going to pass him around and hopefully he wakes up on the way. And if he doesn't, I'm sorry. Sorry in advance. So inside the robot, we have a 2-board stack. And so these are all our custom boards. So we have just two-layer PCBs, and we just stack them together so we can have components on both sides. So we have our programming port. We have an RGB LED, so we can have different lighting. We have our microcontroller, so we have a pretty tiny microcontroller. We have our ports to add display. We have an IMU for inertial sensing, and we have a motor driver. So, this kind of is a really minimal set of hardware for any robot. Any robot needs some sort of brains. Any robot needs some sort of ability to be programmed. And it kind of just needs, that's basically it, I guess. I guess if you want it to be mobile, you need motor drivers. And if you want some sort of sensing, you need the IMU. So a very minimal set of hardware. But it really begs the question, what can we do with this minimal set of hardware? So our first thing was, how do we design faces? So we designed 5 faces, and we want to know, are these faces recognizable for anyone interacting with a robot? So I will poll you all, since this is a good study size group. Do you recognize these faces? Could you name the emotions? Does anyone want to tell me them if you want to engage? Excellent. Yeah. Yes. Yeah. Yeah, great. So this is actually really, really well studied. Turns out facial displays are pretty universal. And even designing this really, really minimalistic set that I could put on a 1/2-inch screen, I can still get the same type of connotation to you all. So that was our first thing. So can we design a set of faces that are recognizable by anyone who goes and looks at the robot? And the answer is, okay, we did pretty good, but we had 5 participants. And if I really want to beef it up, there's more than 10 of you in this room. So now this is really statistically significant. But we need to kind of enhance this. So that was kind of our first thing. Can we get facial displays on a really tiny screen with just black and white pixels? And can we get you all to recognize the emotion? So that part has been a success so far. And so then, now that I have sensing, I have now designed for this robot a finite state machine. So now it has an emotional range and it will react to inputs and outputs. So if the robot came back to life and you are playing around with it and you saw its face changing, you will see that it does things, it reacts to how you are handling it. So the robot starts in this neutral affect. So if you're not engaging with it, you're not putting any sensory information on the IMU itself. It's just going to hang out in the neutral affect. If you are playing around with the robot and kind of gently holding it, it will be happy. So you've got to be kind of gentle with it. And if you then are kind of increasing how you're putting sensory information into the IMU, you can make the robot sad or you can make the robot mad. And if you invert it, you can make the robot surprised. And the reason for doing this all into a finite state machine is to kind of give it a little bit more personality. So, how we transition from one emotion to the next emotion is kind of done programmatically based upon what we put into the IMU. And it's not just, a direct reading of this. So there is this space that you have to navigate. So, if you made the robot upset, how do you make the robot not upset? So it's not just like a one-to-one mapping. You have to put in a little more social work or a little more emotional engagement to make the robot not upset. I'm very sad that it did or didn't.
It did.
Did not. I'm very sad. Um, I did. For some reason, whenever you demo robots, that's when they don't work. Or when somebody's looking at it. It's got to be very important. So this finite state machine kind of gave our robot a little bit of personality, and we kind of wanted to understand, well, how do people engage with it? So we designed a second pilot study to kind of understand this interaction. So we just were here at UB 1 week, and we did like just a regular recruitment method, a snowball recruitment. So we told our friends who told their friends who told their friends to say, come play with a tiny robot. So that's how we recruited people. During our recruitment, we had 2 researchers present who were here to observe, just each person interacting with the robot. The researchers were taking notes about how people were interacting with the robots, and then the researchers cross-referenced each other just to make sure, everything was good. Our interaction protocol, we just told people to just play with the robot. We gave standard instructions, and we didn't really add any additional guidance or input. We just were passive observers. And, that's sometimes a hard thing to do, especially if you're a faculty member. You always want to interject. So our direction, and this is a FOMA modeling this for us. So each participant was asked to interact with the robot for up to 5 minutes and just to narrate their experience. So they could talk about what they are thinking, what they are feeling, how they think the robot is thinking, how they think the robot is feeling. And, we were just sitting there documenting. And after they were done, we asked them to take a quick survey. So we had 4 survey questions, and here are the results. So we had question 1. The robot responded appropriately to my interactions with it. So most people agreed. Most people agreed that what they were doing with the robot's affect and its response was appropriate. We had question 2. The robot's expressions changed how I interacted with it. Were you influenced by the robot's affect? And people really strongly agreed with this. And this is actually like a really key insight that we had from all of this work. The other one was the robot's expressions made sense to how I was handling it. I think for the most part, people agreed with this, but I think the finite state machine kind of threw everyone off. And the last one was I understood how to bring the robot back to its baseline. So I knew how to navigate the robot's emotional state. Based upon the questions we got after as researchers of how was the robot interacting, everyone's a liar here. They didn't know how to do it. They just thought they knew how to do it. So I thought that was pretty fun. So we had the survey, and then our next part was to actually do some qualitative analysis and to do descriptive coding. So we wanted to know about both what is the language that people are using to describe this robot, and 2, what are their actions? So how are people interacting with the robot? How are they physically touching it? And so this is where we had to actually take all of our notes and all of our transcriptions that we took down, and we had to do a qualitative analysis to give some sort of insight. So to start, we know the generalized approach that everyone was using was the robots had some sort of facial expression and responsiveness. Every participant was interpreting that in their own way. And while they were interpreting it, they were constructing a personality for the robot. And this kind of shaped the behavior of each participant. So as participants were narrating their experience, most people were describing the robot's emotional states, and only certain people were actually describing the overall expression. So most people were ascribing some sort of like emotional state, some sort of personality to the robot itself. And we even had one participant who said, this robot is behaving just like my cat. So I think that was just like, it was being a curmudgeon, maybe, I don't know. But for the most part, people were focusing on what makes the robot happy, what does the robot like, what does the robot doesn't like, and what made it angry. And that was actually one of the key things that we saw was, when people are getting that feedback from the affective state about this robot is not happy, it's angry, that was serving as a pause. People were then being like, uh-oh, what did I do? And how do I undo that action? And so even just having that really tiny screen with that really tiny face, we were able to modulate how people interacted with a robot. And, people were just emotionally invested in this cubic inch robot. The other thing that we were doing was looking at the nonverbal interactions. So we wanted to see, as people were playing with the robot, what were they doing? So a lot of people were, pushing and rolling the robot around, tapping, petting, poking, flipping, shaking, rotating, and lifting in the air. And so, we saw most people kind of driving the robot around as a little car. I think the wheels of the robot kind of invited that participation. And then the flipping, shaking, rotating, I think people were trying to find those emotional extremes of the robot. And, I thought that this was also very interesting in a way that, how do we invite people to play with something and how do we make sense of that? So the other thing that we got to do with this robot was public engagement. So we brought the robot to the Buffalo Museum of Science during Engineers Week. Here he is. If you ever come to Buffalo Museum of Science, my group is always there. They love demoing robots, and we always have stickers to hand out. So you can always get something cool from us. So we found some really interesting observations while we were just bringing this robot to interact with the public. And, one thing that we saw was that children were naturally more gentle with this robot. We bring a lot of different robots with us, and some of our robots do not survive the day, but this robot remained unscathed. Children were pretty, sensitive about it. Some kids didn't even want to do anything to upset the robot. And I actually had one student who encouraged a kid to shake him, go ahead, make him mad. And the kid was really really reluctant. So I think that we have the opportunity to do a new Milgram experiment with this. The other thing that we found really, really interesting was that parents were just as engaged, but parents were using the robot as a tool for teaching empathy. So as their kid was making the robot upset, they were going, well, you've made the robot upset. What can we do to make it happy? And so there is this extra layer of emotional engagement and teaching that I never even considered for this robot. The other thing is, there was always that relational framing. My group was the robot's family, and so it needed to go back to his family. That's why you had to stop playing with the robot and we had to leave. But I think maybe that was just a tactic used by the parents to get their kids to move along. And the kid pictured, she came back 3 times to play with the robot. She loved him. So eventually, by the 3rd time, we asked for the parents' permission if we could take her photo in a very, unmarked way. So overall, I would say, there's a big opportunity for public engagement. There's a big opportunity for learning and sort of learning how people understand emotions on a physical object. And then we also took the robot around on a photo shoot in the museum. So here it is with the mastodon, the buffalo, in the architecture, in the archaeology pit over by the Tyrannosaurus Rex. So he had a full day at the museum. And this really kind of brings back to my questions. So what are the trade-offs that I have as someone who builds robots between the simplicity of the hardware that we incorporate and the hardware that we use and the expressivity and the robustness of that social engagement? So some of the next things that my group are doing is we are adding in mobility. So you can have the robot drive around, do little happy dances. And so you can connect that movement to display. And the other big question that we have is how do we quantify engagement? So we had this huge set of, nonverbal engagement between humans and the robot. So how can we understand human affect and how humans are thinking about this by our physical behaviors? One thing that's really interesting in the robot manipulation literature is there's this whole taxonomy of grips. So how do you grab an object depends basically on how you are going to use it. Are you using a 2-finger grasp, full hand grasp? And so how do we kind of mathematically model and predict how people are going to grasp a effective robot and how they're going to interact with it? And so this is a huge, rich data source that I need collaborators to work with me on because I don't do anything with computer vision. I don't know how to work with humans on this type of scale. And so this is a really interesting question. And the scale of this robot really provides that opportunity for people to utilize different grasps and to engage with the robot in very different ways. And so I think, as I kind of wrap up, and then since I am actually nicely on time, the kind of big key takeaways that I have is, from this robot, just making this cubic inch robot with a smiling face offers a lot of empathetic connection. So people see it and they're already invested in the robot itself. Usually when I turn the robot on and I can place it in front of someone, when the display actually works, people instantly smile and then they want to say hello to the robot, but the robot can't hear them. And it was kind of interesting to see that just this minimal set of cues from hardware is able to prompt this perception and prompt people thinking about the emotional states of a robot. And I think that, having all this nonverbal tactile information is a really rich data set that can be explored to kind of understand how people interact with robots. How are they using their sense of touch and how is that modulating their behavior? And so I think that, overall, I'm really excited to think about, what are the design features that I can incorporate? But I think more fundamentally, how do I think about, my investment on design features? So what is my cost of having a screen? What is my cost of having an RGB LED? What is my cost of movement? And how does that return social engagement? And how do I modulate those factors so that I can maybe prolong social engagement, so I can prolong, how people care for this robot? And so there's a lot of these really deep questions that, invite a lot of mathematical modeling and a lot of like human behavior modeling. So at the very least, my group can always make robots, but we always need really good collaborators in order to do these things. So far, this is my team working on this robot. Dr. Fogarty did a lot of the qualitative analysis and has been really thinking about like affect theory and touch. A lot of other students from my group have been robot builders, and I've been working with Afoma, Nwagu from CSE on some of these human behavior factors. And with that, I at least have ended on time, and I will take any questions.
Thanks, Ryan. So sort of tangential, but you did sort of assign gender to the robot. And so did you get any pushback from the children, or did they have different
Only
gender
one
assignments?
person has referred to the robot with female pronouns, and we asked why. And apparently, that had to do with how we designed the face and a lot of the anime style of eyes. So apparently, that style of face connotated a female gender, which is not something that I knew, but most people referred to the robot as a boy. That would obviously, or
Yeah.
yeah, those things would instantly change how people perceive the robot. And I think, if we had more of those gendered expression on the robot, do people interact with it differently too? So there's really a rich set of questions to ask.
All right, we might have time for one more question. Anyone? All right. Why don't you ask one?
Yeah, I would make a suggestion about the surprise face.
Maybe
Yeah.
get Kelin to set up while, yeah.
Yeah.
Also, too, in terms of thinking, touch as an indicator of how they're touch is an indicator of how they're interacting with them too. But it's interesting in terms of engagement in the body posture of the person interacting with the robot. Maybe another interesting place to go. With the surprise, I would make it circular in the mouth, and then the eyebrows up and straight
Ooh,
up. But you
excellent.
may not have the space for that. This also has the potential to do a ton of other kinds of things dealing with people who have difficulties processing emotions. We know that even college students who spend a lot of time on social media have detriments in terms of recognizing subtle human emotions in day-to-day life, and so on. And it's interesting to see how this affected the interactions, even in the other thing. We wrote something a few years ago highlighting what each emotion does, why it's in us evolutionarily. What's the purpose of, anger is to stop something with somebody, blah, 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 blah. But I'll send that along at some point. I don't want to monopolize the questions, but. So let's thank Ryan again, and you'll be sticking around till the end of the hour, and maybe you can engage with him a little bit more. Sure. And yeah, we'll sort of now transition to the second talk of today.
Just okay. Okay, yeah. Thank you. So robot is interesting. So right now I will talk about something which is about teaching. So we have a lot of students and also faculties. Today I would like to talk something about my teaching experience. I teach algorithm course. Right now I try to explore the integration of large language model enhanced proof assistant in the algorithm courses. So why we consider it? What is we started in algorithm course. So in algorithm course, we have 3 key tasks. The task is we have some problems. For example, like this, we have some input data set and we're targeting to solve some problem, get ideal result. And the algorithm course, our task is to teach students how to design algorithms, design the efficient algorithm to solve the problem. And we also somehow like integrate like the structures to implement the algorithm. And the most important part, what we teach is help students to analyze the algorithm. Because you can have a lot of algorithms, but how can we analyze, is it works? How good it is? We need to teach students how to analyze the algorithm to know whether or not it's efficient and is it work. So we teach this course. Most of the time we just teach with lectures, the regular assignment, project. Right now I'm trying to think about, can we have some proof assistant help students to learn the analysis, learn the proof. The proof assistant we introduce here like Lean, Cork, Isabella. The Lean is the one we would like to incorporate for the algorithm course. It's already proved to be useful for the mathematics, software design to verify the correctness, analyze the software. And how can we use it to help help students to learn and the analysis. And the one I mentioned, emphasize here, which is large language model enhanced. Later, I will talk about why we need it. And we know about ChatGPT, Copilot, if you do programming. And for proof, can we use large language model to help us? And can be guaranteed to be correct? Because large language model, we have an issue to know, okay, is it correct? We just guess and we verify person error. Can we have something to guarantee it to be correct? We have Lean Copilot. I will talk about this. And the idea is to know how can we incorporate the proof assistant in the learning process. First, motivation, why we need it. In algorithm course, I teach multiple semesters. I noticed that in the analysis part, especially proof of correctness and complex analysis, students feel it's quite intimidating, time-consuming, difficult to follow, and they would like to implement. So they feel implementation is quite intuitive, engaging, and they can immediately understand is it works, but they don't know whether or not it works for every instance. So a lot of students ask in my class, they would like to have more programming projects instead of homework assignment because they like coding. And although they are not sure about whether or not it's correct, but they like coding. Yeah. So that's a motivation. Can we satisfy student requirement demands and also teach the course content to help them understand analysis? So we are thinking about using Lean, the proof assistant. Lean is both a proof assistant and also a programming language. But it's not like the regular programming language to work. It's like a programming of your proof logic to verify the proof. So if we think about using Leans, we can use Leans to formalize our algorithm as function We don't need to know, okay, how it works for that small instance, big instance. We formalize it, and then we can use Lin to verify it, verify our proof. It's a language for programming your proof and proving your programs. And let's look at two small instances. The first instance, which is very easy proof. Maybe you think, okay, it's too complicated to use a proof assistant help me. I know it. Okay, it's like if we have A and B, then we have B and A. Okay, so it sounds, okay, you do nothing. I know it. But logically, if you have more complex one, how can you verify it? And this one, you will have the hypothesis. Basically, the machine help you to check whether or not your proof is correct. You don't need to do it. But of course, we need to have the code. But how can we have the code later? We will have some way to speed up our coding proof. Okay, the second one may be a little bit more complex, but also still not too complex. It's like we define some function. It's like what we do for algorithm calls. Our algorithm is essentially you implement it as a function. So you have some inputs, then you have some idea output. For example, now my function is like add 0 for natural number. I have n, then I want to add 0. Okay, you know what is n plus 0. Still n. Okay, but what happens if you do some programming, you have small mistakes? And how can you know that you always be correct? And if you have a more complex function, how can you make sure that your function works as you expected? So we need to verify it to prove it's correct as I expected. So I prove the theorem. My function at 0 will get at 0 n equal to n. How to prove it? I introduce this n to be any arbitrary natural number, and then I afford my function. Maybe this one is a simple one, but you have a very complex function. You defined, I afford it, and then I use the tactics from the natural number basics, and I get n. And I proved the right side expected I get n plus 0, then I get n. I know it's correct. What happens if you have some mistake? Then I get this one. In some sense, I design an algorithm. I define a function of my algorithm which have some mistakes, but it still works for some instance, not all the instance. For example, here I have n plus 0. How can I know my algorithm works as expected to get my ideal result n? I need to prove it. If I can prove it, I get the result, but somehow I try to prove it every step. I have my goal, which one I want to prove. At the end, I have the type n plus 0 equal to n, but expected I have my add 0, which is n plus 1 get n. So it's unmatched, then I know it's not correct. So this proof assistant can help us to verify whether or not our algorithm, our function, which is designed to be correct. Okay. That's why I would like to introduce this for the algorithm course to help students to analyze the algorithm, their algorithms in whether or not it's to show whether or not it's correct instead of just informal math proof they struggle with because they know programming, they would like to use programming to verify it. And in Lin, there are also a lot of library you can use. The machine chapel proof system can also be shown to be more accurate than humans. How can it be? Because Lin it's not just verified by itself in its own check system. It can also be verified by other proof systems, like Cork or Isabella, its interactive. And it's a powerful tool. You can explore some null results and theorems in all the undergraduate courses and most of the graduate knowledge courses. In addition, it's an auto review process. When you work for the proof, when you work for the function, you can immediately get the feedback from Lin to tell you which step you expect that to go, but you get another one not matched. Then you know which part you get it incorrect. So you can use it to help you immediately know whether or not I can solve my goals, prove my target. And the library have a lot of tools, and in recent 2 years also extended to have more computer science tools like these structures, computation theories part tools you can use. It's already proved, and then you can use it to build up your own proof. Okay, and the thing is, it looks quite good, but still have challenges how it's used in teaching. It's a tool. It's a new tool. So it's always, we worry about a steep learning curve. How can it be used for a student to use it for the first time? Some students share their thoughts to use it in first time. They notice that the proof, sometimes themselves, like the task itself, looks quite simple. But to prove it perfectly in Lean is quite difficult because you need to know the syntax, you need to incorporate, you need to first understand the proof and then prove it perfectly in Lean. The second challenge is that you have a lot of powerful tools, lemmas and logics, which are already built, which are already in the library, but I don't know it. If you haven't used it before, you don't know what exists and how to build up. So selecting the correct techniques libraries is also a challenge for students or for the beginners. We are familiar with it, but if you're familiar with this, then it becomes easy. But it's still a challenge to introduce it in the class. Okay. Another thing, which is the most difficult part, we learn the algorithm course. We are not learning Lean. Okay, we are not learning the proof assistant. So we are trying to use it along with the course objective instead of learn the tool itself. Okay, we would like to reach our learning objective. And how can we balance with the traditional method? We would like to help students learn proof. How can we balance the content itself and the logic, the tool programming? Because we don't want to give a double challenge for students, learn the content and learn another tool. We want students to complement their study with this tool instead of replace this just learning this tool. Okay. And when we try to incorporate it in teaching, we also need to consider the student background. Not all the students like new programming languages. Some students, yes, but some students feel it's quite challenging. How can we handle such problems? And another thing is that since it's a new tool, we need more tooling support. Our TAs also need to help students with the learning content and the tools to help them get familiar with this. We have a lot of challenge here. But large language model can help us with a lot of part, like maybe release a bit about steep learning curves, and also it can help a lot for us to select techniques and libraries. It will not give you the solution. It gives you suggestions. Some suggestion which is related to this topic, and then you can select, you build up your proof with these suggestions. So you need to know the logic to build up it, but you know something which is already built up, you can attach that in your proof. And it's not it's just developed in recent 2 years, like 2023, they developed the Lean Dodo, and then this year they developed the Lean Copilot from Caltech. The tool, which is not like what we use ChatGPT, like ask, okay, what is answer? Give me the logic reasoning. It's like they give you some suggestions in Lean. You can select to build the proof. But for the long proof, they are not able to give you the long proof because it's still a big challenge for large language models. You need to know how to solve it. And this Lean Copilot just give you a way to search. It's like a search tool, assistant, like a search tool, what is related. And then you need to build up the solution. So here is what
we
demo.
introduced LIN Copilot, a framework that allows large language models to be used efficiently and seamlessly in the LIN proof assistant for theorem proving. It is a package you can import into a LIN file. At any point in your proof, you can call a large language model to suggest the next step, simply by typing suggest tactics. Suggestions are displayed on the right in the info view. Click on one to adopt it in the proof. Moreover, large language models can be employed to give the complete proof. Just call search proof, and the complete proof will appear on the right. Click on it to prove the theorem. Theorem proving is a challenging task. Huge difficulties come from picking the correct lemmas, also known as premise, from a huge mathematical library. To assist with this core task, one can simply type select premise and see relevant lemmas displayed on the right. LIN Copilot can run locally on your laptop with or without GPUs. We have open source all code on.
Okay, but you noticed, okay, they give you a lot of information. Then sometimes students may just want to try, okay, give me the solution, give me a proof. Then you have the AI violation case. We have a lot of concerns like use large language models in the class, finishing the assignment. If we just tell you, okay, you can use it, then we have a lot of problems because some students, they know how to use it, they learn well with this assistant, but some students they cannot identify, okay, is this correct or not correct, then they cannot learn from this assistant. And to incorporate that, we need to think about how can we identify the use of this such proof assistant in the class. We need to specify our AI tool usage policies, which is like we want it to be a learning assistant instead of solution generations. And also, when we do the proof, when we study different type of algorithm, we need to follow the course or assignment specific technique constraints. So you need to have a constraint. We will set up the constraint for the assignment, which set of tactics we build up you can use from this course, not from the big libraries. So we may have some course-specified tactics, which is provided for students. In addition, we need to require students to explain their tactics, their proof, which include explanation or comments for each proof for each lab, and also assignment. For the assignment, we have the auto grader and also oral check-ins to have oral interview to explain their proof. And here we have the some teaching resources which are already developed for teach CS courses. Initially, the first one is from CMU. They developed the course for logic and proof user needs. And in the last 2 years, because of the LIN Copilot development, it decreased a gap of using LINs for the beginners. Right now, more courses are developed for using LINs to teach the proof-related courses. And in addition, more teaching resources are available like notes, textbook, games, and auto graders. For all of these resources, then I'm thinking about how can I incorporate that in the algorithm course. The target is to help students analyze the formalizing time, space complexity. In addition, we learn the algorithm. How can we help students to learn how to prove the algorithm formally? And to incorporate it, since it's the first time try to incorporate it, we didn't put all the part in the algorithm. We still have the regular lecture time, and we have the proof system assignment with or without large language models. And for each assignment, we have the pre and post to investigate how the student understand for each part. And to incorporate the LIN assistant, we have 3 dedicated components. The first one is we have the introduction to get students understand how to use it in the algorithm course. And then we have some proof exercise, which is incorporated with the content we studied in the course, at the end, we have a lean proof project for the algorithm, big algorithm. For the introduction, it's quite short in the first week with some introductions and example proof for algorithm course, and also have a talk about how the evolution of computing tools to modern machine learning and the proof assistant. And then for understanding students the habit of using large language model, we have the assignment with surveys to know their habits. The first one, we would like to understand how their willingness to use large language models. So about 81% of students will use the AI assistant in algorithm course, and 19% students say, no, I don't want to use it. Okay, we allow both in our assignment. And then we also have reflection like students' concerns regarding use of the assistant. You can see that the most part they concern about the AI tools will not give the correct solutions, may generate incorrect explanations, and also have some students concerned about the academic integrated policies. Interesting part is that whenever we have the assignment, we identify the small task for each problem assignment, like collect the data, develop strategy, processing data, obtain the solutions for the corresponding problem. For example, the assignment we have is to get the maximize non-overlapping selections for the cost schedules. The most difficult part student identified is how to verify, how to prove their solution. That's this part we get selection to use things to prove their solutions. And to use it to prove some big project, there are lots of gaps. So how can we build up each step? We first give some lean proof exercise. The first exercise we give have all of these topics, like the basic algorithm notation, synthetic analysis, basic algebra, induction proof, and some one-step proof and two-step proof. We identify different level of proofs. And you can see from these grids, the first one is we can understand the notations more easily. And of course, this is an easy task because they just need to define it to verify the notation. This is an easy task. Everyone can do it. It's also like expected. And still the proof, induction proof is most difficult part. To get a long proof, even with AI assistance, it's difficult. And if we separate it to be some small step proof, one step or two step, give them tactics examples, or without tactics example, give some new tactics, they perform different. But this performance is kind of like expected. They know something, they get example proof, they can do some new proof which is related. If they don't know this before, it's difficult for them to explore the new one, although you have the suggestions. Okay, and from all of this exercise, we have interesting findings to know that actually for all of this lean exercise, students will be more confident about their submission. Although they have some parts they don't know how to solve it, they are confident for the part they finished. And for the part they don't understand or they are unable to solve it, they just state, okay, I can't solve it. They are not trying to give something which is like the knowledge they don't know. So that's an interesting finding. Students can identify their gaps in knowledge. Okay, and also we have exercise which have the wrong theorem. I didn't give them the correct theorem. I asked them to prove the theorem. More than 96% of students identify the error. And the error either corrected or provided the counter-example proof. That's not expected because the counter-example proof we haven't covered, but they try to provide a counter-example proof. They explore the lean proof by themselves. And I mentioned that because right now, all the large language models, Lean Copilot, they are unable to give you the counterexample for the theory you stated. They just continue to give you suggestions, tactic to prove it. They recognize it's correct. Okay. But students, they try it and they notice, okay, it's not correct. They get a correct way to prove it. They get a correct theorem. And in addition, with this proof programming, they can deeper the understanding of the underlying proofs. The student give feedback that they try it, they immediately try different techniques, different logic to prove it, and they deeper the understanding because they notice that only they understand the logic, they can get the correct programming proof. And the final part is we didn't require students to give the detailed proof sketch or the prompt they used to get some suggestions. But the students, 20% students, they provide a very detailed reference about how they solve the problem. And for each step, how's the understanding their goals in the steps. And for this part of students, they get high performance for the grades for this exercise. And still, there are some complaints and comments about how to use it, how to use these tools in algorithm course. The first one is student ask for more proof example. Maybe you sound it's not very interesting, but that's interesting thing in algorithm course because before we use it, students ask for examples. They always ask for instance example. They are not asking for proof example. They would like to look at some real case instance. Give me 3 size problem, 10 size problem. I try to understand the problem. But now they already understand problems. They try to ask for proof. They want to understand the proof. They ask for proof example to prove their own programming proof. Okay, I think that's quite interesting because now students seems like they already cross the barriers to know the general problem. They are asking for the general idea to prove this problem, not prove it from instance. Okay. And still, we have the learning curves. Some students have the comments that they need more time to handle this new program because they do not have this experience before. And that's something we also need to consider in the future semesters when we would like to continue to incorporate it. Okay, that's what we found from the exercise part. And the second part we incorporated at the end, we hope students can finish a BIM project, proof their algorithm formally with the assistant. And the project will include 2 parts. First, programming their algorithms. Okay, this part is students, they like it. They just change the programming language from Python to this leap. They can programming their algorithms. The second part, which is which is new because initially they tried to have the paper pen proof. Right now they need to finish a programming proof, which requires deeper understanding about how to build up the proofs and make it work. Because for the hand pen paper proof, no one checks whether or not you have small part of logic missing. It does not work. But this one, the machine checks. Machine will tell you, okay, this part does not work. Okay, you need to fix it. So they need to finish this part. It's still an ongoing project until the end of this month. But students give feedback that, okay, before I can complete this project, I already understand it deeper than before because I know, okay, I need to make it work, then I need to first understand in math way. It's more demanding than the traditional proof and well-structured proof format. And what we can get from this small try this semester. And I noticed that to handle the learning curve, we may need to provide some recitations or recorded videos for students. Some students, if they have difficulty to learn this new language, new proof language, they need some step-by-step example proof, especially for the early stage like student. It's designed for support students facing the learning curve. In addition, when we design the example or exercise, we need to structure from the basic to advanced to different difficulty levels, and also include some correction focused exercise. For this correction focused exercise, which is students, they feel quite excited. Okay, I found the error. I found this one. I can correct with this way, and this is an easy theorem I can prove. Or I gave you the counter example. It's essentially the proof logic. They get it from such exercise. And the last one, which is also suggested by students, we need to build up the course-specified proof tactics. And it's not just like the instructor tell you, okay, what text we can use, and what we have, we only use that. For algorithm, you solve problem, you can have different algorithms to solve the problem. And the students can contribute to the tactics, the algorithm, the course tactics. We may build up a way to recognize and credit student contributions in developing these proof tactics, which is kind of like a proof version LeetCode. Like students all practice their coding in LeetCode, but how about practicing their proof? Build up some tactics and contribute to this course, and also their future learning. They build this library and they can use it in the future. Okay, and that's all I want to share today, and thank you.
Yep, we have time for a couple of questions. So in terms of the time it took for you to sort of set up the course using these tools, how did you feel about it? Like, I mean, so we listened to a lot of the opinions of students and the problems they faced, right?
Yeah.
But as an instructor and being able to incorporate this, what was your experience?
Yeah, for me at the beginning, I feel I also have the same feeling, like I don't know it before, then I do not look at any tools, I just try it by myself. I feel, okay, it's difficult. I don't know how to use the syntax. I don't know where is the lemma. And then I look at some online resources and I immediately get into it with some small tasks. There are already a lot of resources available. I start to use it and try to incorporate it in class in the last year. And after one semester, I think I can use it right now and also use it in my research, not just in the course, because if you look at the search proof assistant, you may realize right now the large language models, they are training, they also have these lean verification procedures in the training model. In addition, we can use it in both directions. Use lean in the training model and the training model to help the lean to study lean. Yeah.
So from your learning experience, like in trying to incorporate this into other courses, would you have any suggestions of how to do that? Like, I mean, is there a cheat sheet for how other people could incorporate this into other courses, and what sort of courses would be more conducive?
Yeah, so for now, I think this tool, which I found right now, from my aspects, I found it's very interesting for the series CS course, but not immediately for other courses, because I haven't taught other courses before. I'm not sure whether or not it can immediately incorporate, but I feel it's very useful for series course, series CS course, and to develop first we need to develop the environment for this course to incorporate the knowledge we target in the courses, and programming in, and create example proof and create exercise. It may take some months for the instructors. It's a lot of work, but after it's built in, then it's easier to use it again to continue get the contribution from the students' tryings. Yeah.
Okay, that's great. Any other questions?
Yeah, I guess. People on the.
You don't feel like the introduction of the language model would necessarily make the course easier? Or do you also believe that in conjunction with the introduction of the language model, it would allow professors or instructors to adjust the course accordingly?
Okay, that's a good question. It depends on the courses. So right now, what I incorporate is an algorithm course, which is like for CS student studies. It's kind of like in their third year, or I will teach it in the graduate students. They already have a knowledge about programming. It's a sense that they learn a new programming language. But if we incorporate in this structure course, which is already well incorporated in many universities, and for this structure course, they start learning more languages, so they will teach more about the link program. Yes. Thank you.
All right. So let's find these people again. Same thing, there's some snacks on the table there.